Hello and welcome to lesson 7.3, derivatives of inverse trigonometric functions. Well, before we actually start with some inverse trigonometric functions, we're going to actually look at how inverse functions relate to their original function. So, to begin with, recall that f inverse of f of x is equal to x. Now, if we use this, what we can do is we can find the derivative on both sides of this expression with respect to x. And what you'll notice is you have to use chain rule, so f inverse prime of f of x times f prime of x is equal to 1. And then you can rearrange this so that you can write down f inverse prime of f of x is equal to 1 over f prime of x. Or if you wish, f inverse add a prime of y is equal to 1 over f prime of x. So what you can see right there is, let's say we take this point right here at 1, 2. The slope at 1, 2 is, let's see, it's 1 unit over, 3 units up. So what you can see is that slope, f prime of x, is equal to 1 over 3. Well, f prime at 1, actually. Now what you can also notice is something similar happens at this point 2. Actually the slope is 3, not 1 over 3, it's 3. 3 over 1. Now the slope at the f inverse at that same spot is so f prime at the value 2 is equal to 1 over 3, which is related to this value right here. This is a concept that they use at least once or twice within the AP exam. So using this, we're going to continue on and find derivatives of inverse trigonometric functions, which turn out to be a little bit more challenging for some people. So to determine the derivative of y equals sine inverse of x, what we're going to do is we're going to rewrite it as sine y equals x. And we're going to find the derivative on both sides with respect to x. So the derivative of sine y is cosine y, which you have to multiply by dy over dx. And the derivative of x is just 1. We rewrite dy over dx as equal to 1 over cosine y. Now what you'll see is on the right hand side, this expression is actually in terms of the expression y. It's not in terms of x, like this thing is. So we're going to have to rearrange this and change it. So in order to do this, something I want you to remember is, I want you to note that we know sine squared x plus, well, actually let me use something other than an x. Sine squared theta plus cosine squared theta is equal to 1. We know this. And this helps us relate sine to cosine. So what I'm going to do is I'm going to rearrange this expression. Sine squared theta is equal to 1 minus cosine squared theta. Or you can also write it as cosine squared theta is equal to 1 minus sine squared theta. Now the second one makes more sense. So cosine theta is equal to the square root of 1 minus sine squared theta. So you'll notice cosine y, therefore, is equal to 1 over square root of 1 minus sine squared y. Almost wrote a theta. Let's change that sine squared y. Now, originally, we have sine y is equal to x. So, that means sine squared y is equal to 1 over square root of 1 minus x squared. And now we have the derivative of y with respect to x in terms of x. And that's ultimately what we want to be able to do. Okay, so let's move on, try some other ones. So we're going to try to find the derivative of y equals tan inverse of x using similar properties. So let's try writing it as tan y equals x first. We're going to find the derivative with respect to x on both sides. Now remember, the derivative of tan y is secant squared y. Again, we've got to multiply by dy over dx. And the derivative of x is, again, 1. Excuse me. So, dy over dx is equal to 1 over the secant squared of y. Now, again, we don't want to have it in terms of y. We want to have it in terms of x. So, again, I want you to recall sine squared theta plus cosine squared theta is equal to 1. Well, yes, this trigonometric identity is helpful, but in this expression, why is it helpful? Well, we want to change some things into secant squared y. I can change the 1 into a secant squared by dividing by cosine squared. So that's going to give me secant squared theta. But if I divide everything by secant squared, cos squared theta, this one will turn out to be tan squared theta. This will turn out to be 1. So now I can change this expression into 1 over tan squared y plus 1, or, if we remember, tan y was just equal to x, so dy over dx now becomes 1 over x squared plus 1. Now you can find the derivative of cosine inverse of all the other functions. That's just to show you. Derivative of secant inverse of x turns out to be this expression, which looks similar to the derivative for sine inverse, just with some small changes. As you'll notice that x squared minus 1 underneath and the square root has changed. Also, you're multiplied by absolute value of x. Now, don't wonder that the derivative of cosecant inverse of x looks also exactly like this one, but just with a sign in the numerator as a negative. And the derivative of cosine inverse is the same as sine inverse, just with a negative in the numerator. And then you could probably guess what the derivative of cotangent would be. So to figure out other derivatives, we're going to use some other identities. Now, you may remember the cofunction identities. These are inverse function, inverse cofunction identities that you see right here. So that you can see how these are related maybe to sine x equals, cosine of pi over 2 minus x. It's similar to that expression, just because these are inverses, of course it's a vertical translation instead of a horizontal translation. Some other identities that could be very helpful are these ones. These ones are called calculator conversion identities. It allows you to change a secant inverse into a cosine inverse just by noticing how the variables change. And again, these aren't too difficult to figure out and realize. So, what we're going to do is we're going to do this very last problem here. Now the derivative here can be fun to figure out, plus cosecant inverse can also be difficult to figure out. So what we're going to do is we're going to change the d over dx right here of cosecant inverse of 3 over x squared. And what we're going to do is, again, you're going to realize cosecant inverse is the same as sine inverse of 1 over x. So that means this is the same as finding the derivative of sine inverse of x squared over 3. Now the derivative of the x squared over 3 is much easier than 3 over x squared. Yes, it's not too difficult, but it's a lot easier. And also, we don't have to figure out what cosecant inverse's derivative is. So, using what we know, derivative of sine inverse of x is 1 over the square root of 1 minus the expression squared. But you also have to find the derivative with respect to x of x squared over 3, because this is just chain rule. This has a function with inside of another function. So now that we have this expression, we're just going to simplify it. So this is 1 over the square root of 1 minus x to the 4 over 9 times 2x over 3, or 2/3 of x if you wish. Now we're going to continue to simplify this, and it's just the simplification part of it that can be tricky. Under the square root, I'm going to change it so it's 9 minus x to the 4 over 9. Make sure that square root is longer so that it covers the entire expression. Now the square root of 9 is just 3, so that 3 with this 3, that square root of 9 and that 3 will cancel. So now you get the expression 2x over the square root of 9 minus x to the 4. And there you go. There's the derivative of that expression. And thus concludes this lesson.